Okay, let's continue on how we can fabricate the metals. So there are two ways on how you can fabricate your metals. First is a blacksmith uh, process, which is you hammer a metal, or we call it forging process. If you watch the movies, the ancient movie English movies, they will, like, if you want to make the swords, they forged the metals, by using hammer, right? So that is the process of a blacksmith. And the second one is you pour the molten metals, which is in liquid state, and you pour it into the mold to get it what shape that you want. Okay, so the forming operation, either you do hot working or cold working. So hot working means that the formation temperature high enough for recrystallization, and but a whole working has large deformation. Okay, um, means that hot working you can deform it in a large manner. Okay, however, the cold working, the deformation process is below recrystallization temperature. Okay, and the strain hardening will occur, but it will cause in a small deformation. So that is the difference between hot working and cold working. Okay, this is how you fabricate a metal, whether by forming, is that you hammering or you stamping. Okay, it can be used in wrenches or crankshaft. Means that you put it in a die and you put a force in it, or a drawing method. Drawings, either you want to do roots, root form or wire form or tube form, whereas you make in you force you pull the metals. Okay, you pull the metals, so we call it drawing process. Or rolling, you roll the metals. Okay, you roll metals uh, for making beams or rails. Okay, rails or plate or sheets, you do rolling, either hot working or cold rolling. Okay, and also extrusion to make rods or tube. Okay, you do extrusion. Okay, and then you can do casting as well, mean that you put in a mold, and you melt it in a furnace first. Okay, so the you have to have liquid metal first before you put in a cast. And basically it is a common process and inexpensive. It can give a good production of shapes. You can shapes in any shapes that you want, but it will result in a weaker products because they will have internal defects there. Okay, but this is a good option for brittle materials. Okay, you can just pour it in the mold, so that we call casting process. And there is a type of casting, either sand casting. So we do, if you remember in the workshop, in your workshop subject, okay, I think you will do this. There is a mold that have a sand in it, and then you put sand within that mold. Okay, and then you put a molten metals, so you got a shape that you want. So why we use sand? Because the sand can stand high temperature, because you know that this molten metal is very high temperature, which is more than 1600, and only sand can withstand that temperature, and it's also inexpensive, and it's easy to mold, means that you can just put it in the mold, and it can follow what shape that we want. Okay. Okay. Yeah, this one I think you can read yourself. And okay, there is a miscellaneous process on metal fabrication, the powder metallurgy or welding. Okay, and here this is how you process metals. So you got a metal, so you want it to be a properties that you want. Okay, so you now you already get your metals, okay, in a solid forms, but you want to anneal it. You want to have the properties that you want. So first you can do annealing. Annealing means you heat to temperature, we call it T anneal, and then you cool slowly. Okay, there are types of annealing. First is stress relief. Okay, stress relief means that after you do a molding process or forming process or casting process, they will have a stress inside. Okay, the metal also have a stress, right? So the stress is come from a plastic deformation, or you do non-uniform cooling. Is that you heat your metals, but a cooling is non-uniform, so the metal will have a stress. And also the stress will come from the phase transformation from austenite to ferrite to cementite. All of them will result in stress. So if you want to release that stress from metal, you do annealing. Okay, okay, then there is a process anneal. Process anneal is a result of effect of cold working, okay, either by recovery or recrystallization, or spheroidize. Okay, spheroidize means that you want to make a very soft steel to get to easy machining. So you just heat it below TU tectoid, okay, and hold it for 15 to 25 hours, so you'll get a spheroidized steel. Or you can do full annealing to get a soft steel for good forming as well. Okay, you just heat it to get austenite, and then you furnace cool it. Means that you put the sample in the furnace uh, to cool it, not to heat it, but to cool it to obtain coarse pearlite. Okay, if you got a coarse pearlite, you will get a soft steel. And then you also can do normalizing. Okay, normalizing means that you deform the steel with large grain. So the steel have a large grain, so you want to normalize it. That you heat treated it to allow recrystallization. Means that now you want the steel with large grain. Okay, you just have to treat it by heat it. Okay, and the grain will recrystallize it, recrystallize, and it will form smaller grain. That is how normalizing process is will result in. Okay, so here is the process how you want to do full annealing, how you want to do quenching or tempering. So full annealing, you just heat the steel is at around 760. So you would cool it slowly. Okay, you will got pearlite. Okay, pearlite. And quenching means that you cool it very fast, and you will get martensite, and you cool it at a furnace for a long time. Tempering, which is tempered martensite, where you cool it very fast, which is quenching. You got martensite, and you heat it. You cool it slowly. Okay, you cool it slowly. After you got martensite, you cool it slowly. Okay, and then you heat it back. Okay, here means you heat it back around 560 to 400 400 to 500, and then you cool it, you hold it for some time, and then you cool it very fast. Then you will get tempering. Okay, that is the tempering process. You got tempered martensite. So now, how to measure the hardenability of steels? So what is hardenability? It is a measure of the ability of the steel to form martensite. Okay, so you know that when the steel have a martensite structure, it has a very high hardness, right? So how to determine the hardenability? So you have to do experiment where we call it Jominy and quench test. Okay, it is used to measure hardenability. So what you will do is you put your specimen, which is the red one here is your specimen, where you heat it at austenite temperature. Okay, austenite phase. Okay, and then you cool it by putting the water jet here, which is 24 degrees water. So you will determine the hardness of the specimen from this point up to this point. So logically, here it will cool first, and the temperature will decrease as you increase the length of the steel, because this part is cool first, right? So means that when we're going back to the TTT diagram, so here it will form martensite first because it is rapidly cool. You cool it first. You cool it earlier at this part. Okay, so this will form a martensite first. So this will have high at this region. This will have high hardness compared to along this steel. Okay, so at from this part you will get high hardness, and by increasing the distance the hardness will reduce. Okay, if you plot the graph, you will get the high hardness at this point near the quench end, and while you increase the distance from the water jet, the hardness will reduce. You got what I mean? Okay, so here the hardness is high. By the distance increase, the hardness will reduce because the time for the steel to cool is long. It will not form martensite, because if you want to form martensite, the time taken should be very fast. Okay, now the reason why hardness change with distance. So like I said before, if you go back to the TTT diagram, so here is the steel. Okay, this is the water jet. The water jet at this point means that the distance is very from this point, the distance is very near to the water jet. So at 0 inch, which means that the water jet is very near to the steel, you can see that, okay, this is the graph, the steel form 100% martensite. So as the distance got far away from the water jet, it will touch perlite. Okay, so the steel have martensite and perlite, so means here the hardness become lower. Okay, this is the graph of hardness. Okay, the hardness become lower, so the more distance from the water jet, the hardness become more low. Okay, because they already got a fine perlite. So now you can see the lowest hardness, which is here, you will got 100% perlite, where the distance from the quench end is very far. So it will not form martensite.